Okay, so hello everyone. We are RoboSub Team 1. My name is Aren Petrossian, and I have with me Anthony, Carlos, Christian, Edgar, Edward, Jose, Nahom, Stephen, and Tianyu. Our faculty advisors were Dr. He Shen and Dr. Mike Thorburn. Our team has 7 mechanical engineers and 3 electrical engineers. On the next slide, I'll show how we decided to break our team down. Our mechanical engineers have a structure team, which build the body of the robot, an actuated system team, which builds several actuators that our robot will use, and a specialized systems team, which has 2 unique systems that have never been tried before by our Calcutta team. Our EE side has a power distribution team and a data acquisition team for some of our special sensors. We also have a CS, senior design team, that works on the programming of the robot and making sure it's autonomous, but they're separate from us. So for our entire team, we prototype, manufacture, assemble, and test an AUV to compete in the 26th annual RoboSub competition, and our goal is to be in the top 5. These are some of the tasks from last year. You can see in the top left, there's a bin task where we have to use a claw to take the cover off of a bin and then use our ball dropper to drop a marker into it. There's a path in the bottom left that our computer vision side of the CS team can use to navigate. There's a buoy task in the middle where our robot just has to choose one of the buoys and bump into it. And there's a torpedo task on the far right, where we have to shoot a torpedo through one of those small openings. For the 26th annual competition that we'll be participating in, it's going to be happening in the Transdeck in San Diego, which is a Navy testing facility shown on the right. And on the left, you can see a top view of this Transdeck where they broke down where they'll be placing certain tasks, and they put icons for what those tasks would be, like the gate, the buoy, the dropper, all of those different tasks. Here we can see a photo of Lantern, our robot. This was what the 2022 last year's senior design team had left off on. And on the next slide, we show our 2023 robot with all of the changes we've made, and we'll talk in this presentation about what those changes were and why we made them. But I'll continue by passing it on to Tianyu to talk about the frame.
Thank you, Aren. Hello, my name is Tianyu Ma. So I will talk about the frame part. So for frame, in the competition, the frame will be provide adequate support for the critical component and optimize to avoid stress concentration to withstand load without any deformation or failure. And also for when we put the vehicle, you'll be very physically in the water. So for red picture, it shows the last year senior design team, they design. So we can see they use a lot of the 3D print part, but this is not very good design. So next slide, please. So this year we just overruled last year design because at the beginning, our advisor told us to avoid unnecessary intricate geometry and higher risk point of the failure. So do not use a 3D print. And also because the frame will be among 8 structure, so the frame will be give more and strong the mounting support. For this picture, it shows this year new design. We use aluminum safety one, cutting and bending and welding. We got this. Next slide, please. And when we drawing from the SolidWorks, we set the K factor is a 0.5, but in our real life, it has some various condition. So we just try to bend for different thickness. For this picture, it shows the result after bending. So we can see it's a little bit crack that we don't want to appear in the competition. So we use the welding to reinforce to the bend and to security the joint. Next slide, please. And for the bottom cage, it will be mount a lot of the component and sensors. So we use the FEA analyze to make a simulation. We put the load as 40 pounds, and we got the result. We can see it's a safety and no significant deformation. Next slide, please. And after we got all the cage from the outside factory, so we make assembly, and the last picture it shows the finalized version. Next slide. And also we want to mount the camera to the hole, but we didn't see any precision. So because the hole is a no screw hole, and also lucky this year we got the camera this size is very small, and the weight is very light, like it's only 17 grams. So it will allow us to use a 3D print to make. And also we don't want to drill the hole as a hole because it will cause the leak. So we want to save progress time and to allow the CS team to easily remove it and put it. So we use a heavy duty Velcro, like it's 10 pounds to attach the camera bracket with the hole. Thank you. This one frame part that I will be passed to Carlos.
Thank you, Tianyu. So I was tasked with providing a hull. The purpose of the hull is to protect all the electronics from the water. It needs to be water sealed. It also provides support for the legs and the thrusters and actuators, so it has to be strong. So for this, we're going to provide some FEA reports, and we're going to do some water testing for the sealing. On the left here, you can see the requirements for competition. It has to float, and there's weight requirements, so it's beneficial for us to reduce weight, and also there's size requirements. We're passed on from the previous years. We received the hull, which you can see here in this picture. So it still needed a lot of work, and this is what we started to work with from the beginning. Next slide, please. So the first thing I did was start to analyze the buoyancy forces and the weight distribution. I took the weight of all the different components, and so it ended up being 17 pounds of negative buoyancy. That means that we needed to reduce the weight. Next slide. So the first thing I did was to create some cutouts on the hull. And this significantly reduced the weight. It was approximately ½ inch thick, and I reduced it to ¼ inch thick. And of course, now it needed new FEA analysis. And also, I changed the design of the lid, also reduced the weight of the lid. Next slide, please. So the past couple of years, you can see here the different designs from the previous years. This past year, part of the design process was to change everything to 3D printed for this past year. And so I looked at the report, and we decided that the durability, the 3D printed was not meeting what we were looking for. We wanted this sub to last a couple of years so that computer science can have a sub in the beginning of the year so they could test their code. So we needed to last. So the first thing I did was try to transition into making the parts out of aluminum, machined in the CNC or mill, but then weight became a factor, and also the contour shapes were too complicated. So I decided to propose a new design, and after meticulous review meetings, the team finally approved it. Next slide. So this is the new design. and it was designed prioritizing the reduction of weight and manufacturability. Next slide. So it's made out of aluminum sheet with several cutouts to keep weight to a minimum. And also it features a universal mounting system where you can mount the sensors and actuators anywhere on the cage that you need. And there's no need to drill additional holes into the hull. And you can, there's several rigging points, and the legs are really strong. And so it was looking good. Next slide. So here, of course, we needed some new FEA analysis, and with a factor of safety of 5, and it passed. There was no yielding. During the modeling, I used sheet metal modeling that allowed me to easily flatten the sheet and produce the G code that was needed for water jetting. Next slide. So next was the manufacturing. So manufacturing with Blake. So initially there was a lot of back and forth, a lot of refining of the engineering drawings. It was very useful firsthand experience as far as learning about the tool passes and the limitations of the machines. And here you can see Blake has a setup for a horizontal mill because the part was too big for our CNC. And on the right, you can see me hand tapping. There was a lot of screw holes to hand tap. Next slide. So I was under a lot of pressure to have this completed for the CS team to have a bot to work with, and also my own team to have a bot to work with. So during spring break, I finished up the water jetting, and I cleaned up the parts after water jetting, and it still needed a little bit of fixing. And of course, I always did some fit check to make sure the parts were still fitting correctly after every single step. And I completed the welding, the bending, the welding, and the anodizing. Next slide, please. So also part of my tasks were to design a carriage for the inside of the hull. And this is going to mount all the electronics. So it features 3 different modes. The first mode is to pretty much be structurally sound for all the electronics. Mode 2 is for when you're installing or troubleshooting, and you need to look at all the electronics. And mode number 3 is for a competition. You can easily swing open the motherboard so you can access the battery and quickly swap out the battery. Next slide. And this is the build for the carriage. We used I did some laser cutting of the acrylic. It has carbon fiber rods, and it has 3D printed part components as well. We did a lot of soldering, several hours of soldering. But during that time, we noticed that it was a good design because we had accessibility to all the electronics. Next slide. So finally, we assembled the sub, and we had to do a vacuum test. And it was very stressful because it was a year-long process of designing, and then we had to make sure that it didn't leak into the electronics. So there were several points where it could leak, including a big O-ring that it was between the lid and the hull, which I had to use the Parker O-ring handbook to make sure the O-ring was the correct size. And I had to calibrate the latches to make sure the compression was right. And here you can see the vacuum pump in action. Next slide. So this is our first pool test. And we threw it in the water and it didn't leak. So we're very happy. And it also was positively buoyant. So it was a huge success. But however, there's many more tests to come. Next slide. And this was our first photo shoot. This is our sub looking great. And with that, I'm going to pass it on to Edward Razo for the robotic claw.
Thank you, Carlos. So for our claw, so I was in task of researching and a good cloth that can match us with our AUV. So you can see a picture of our cloth from 2022, side of the cloth. And so I'll go down to design and functionality. So the function of the cloth is an actuator device that should be capable of picking up objects, but also opening containers. It consists of two servos, two MG99R6. The cloth should be lightweight, less than 2 pounds, sturdy and waterproof. And for the purpose of our cloth for the competition, should be able to pick up objects, mostly bottles, drop it out at a said location. Our cloth should be able to open containers and move covers for us to receive full points. And you can also see two designs of our cloth for the spring and a picture of our final design of the cloth. Next slide, please. So at first, we initially thought it was a good idea for the claw just to only to pick up the claw, so just having a motion of and close. But another suggestion was that having the claw the ability to rotate in case the bottle falls down or tips over when the AUV is going towards the object. And another suggestion was also to enlarge the claw's gripping ability, since we're not sure if the bottle diameter will be the same for this year. And for the dimension of the claw, with the gearbox itself, it gives it a 12.17 inches in length, a claw width of 3.32 inches, and it weighs at 262 grams, and that's equivalent to 0.56 pounds. Next slide, please. So before commencing with the tests, I first put the claw in a water container just to see if it was water so tight. And you can see the video. You can see the video that it's in the pool. I'll do a repetitive motion of open and close at 4 feet. You'll see it soon in the video. So far, it's been there for 45 minutes. There hasn't been no sign of water entering the servo, and that's a plus. And it looks like the buoyancy force does not reduce the motion speed of the cloth for its repetitive motion. Next slide, please. Lately, in the late in March, we have received updates to the claw rules and a new challenge as well. So it was pretty much a deciding factor to actually change the design of the claw, both the claw and the gearbox. So the gripper itself has been shrunk. So the claw width is now 1.19 inches. The length itself, it's been reduced from 12.17 inches to 2.54 inch in length. And now it's currently weighing at 1.08 pounds, still less than 2 pounds. And we'll commence with more testing in the near future. Next slide, please. Now I'll be passing the torch to the marker dropper. All right, Steven.
Thank you for that, Edward. So my name is Steven, and I was working on the ball dropper for this semester or this school year. The purpose of the ball dropper is to achieve one of the tasks of the competition, which is to drop two markers markers inside a bin, and it allows us to have two markers at any given time. One of the design considerations for this design was that we wanted it to hold two markers as compact as possible to reduce the space that it occupied. We wanted it to be easily reloadable, and we wanted it to be easily manufacturable and at a low cost, so that if anything broke or if we had to redesign for any given reason, we could do so at a very cost-effective way. So we also wanted to keep in mind that the mass and the volume would not exceed any more than what we had already designed for, which was half a pound, and the space that the markers could fit in was about 2 inches squared and a height of 6 inches. Furthermore, the servo that we would be using to actuate the dropper needed to be waterproofed, and that was done so using dielectric grease inside of the inside of the servo, so that the water wouldn't penetrate inside. Next slide. So going off of the previous year, we wanted to try and maintain some as much as the design that they had, to see how we can continue on. And so initially we decided to keep it vertical and just change the mechanism that actuated the drop. And so we went with kind of a lever mechanism that released and also locked the marker simultaneously. But that was done to address some of the concerns of jamming from the previous year, and also to limit the actuation angle of the servo so that it wouldn't draw too much power. Furthermore, eventually after some discussion, we decided to go on with horizontal markers so that they would be both side by side. That would reduce the overall height of the dropper and also reduce the volume by decreasing the markers themselves. And so in the bottom, you can see both the vertical and the horizontal droppers. Next slide. So the new markers were kind of looking like projectiles from like a bullet or something like that. And the size of it was 1 centimeter squared, or a radius of 1 centimeter. I mean a diameter of 1 centimeter. And the buoyancy of the marker was 1.23, and this was mainly dictated by the material, which was PETG. It was 3D printed, encasing a marble at the cone. And there was some stress analysis to just make sure that it wouldn't we wouldn't decrease too much the wall thickness, and it was well above it didn't exceed the yield strength of the plastic. And so the final design reduced the overall volume and decreased the material usage, and this was done so optimizing using SolidWorks. We decreased the size of the marker, and we reduced the actuation to not at least 25 degrees of rotation for each marker. Next slide. And so the results were that the markers and the droppers together weighed 67 grams. When releasing the markers at a pool at a depth of 4 feet, it deviated 1.5 inches at a depth of 5, so it had a 1 foot of travel. And so yeah, next slide. And with that, I pass it on to Edward, Jose.
Thank you, Stephen. My name is Jose Lares, and I'm in charge of, my task was the torpedo. So a problem definition, we're going into competition and to the RoboSub competition in San Diego for the 2023 year. Some of the product requirements, one of them was a consideration for the competition that it must not weigh more than 2 pounds. The torpedo must bear the name of the school and must use a school logo. Also, the torpedo must not bruise a diver, and it should be designed to be safe and not harm a swimmer while the torpedo is shot. Also, the torpedo launcher system must be autonomously controlled by the robot. As you can see, we have markers that will be used in the 2023 RoboSub competition. We must fire the torpedoes at 1 meter of distance and hit the target. To the right, you see the launcher, and to the right bottom of the launcher, you see the torpedoes that will go into competition. Next slide. For this slide, I conducted evaluation of the current design. The current design consisted of Senior Designs 2021, which they already had a torpedo, but they didn't actually test it under water or at any body of water like a pool. So the decision was made to proceed with the implementation of the current design. To the right, you see a drawing of the torpedo. The torpedo must have dimensions equally to the torpedo launcher, so it would be easy to mate and easy switchable during the competition, and so that it doesn't slide while the robot's in the water. One of the properties that the torpedo must have, it must have a length of 119 millimeters, inner radius of 16.2 millimeters, and weigh less than 5 grams. Next slide. So in this slide, I conducted an experimental method. I took a bunch of equipment I had here laying at home, like a tripod and some cameras. So I prepared a control filming environment for the torpedo test, applied a launcher compression of 50 psi to generate a force to propel the torpedo. I also used a logger data software that collects points. Logger Pro was the software that I used to document the X travel direction of the torpedo. I added calibration sticks and the X axis in the software, inside the software. And then from there, I determined the average velocity approximate to 16.7 meters. And to the right, you can see the equipment, how the setup, but that same setup would be used underwater inside the pool at a depth at like 3 feet from the ground up. To the right bottom, you see a graph and the logger software. Next slide. For this slide, I conducted some research on how to build the torpedo, how to manufacture what plastics to use. I found through a TA that gyred infill pattern provides balance between strength and weight. I used an infill of 50 to 65%. Was considered. To the right, you see an image of various torpedoes printed at different infills, and to the top of those 3D printed torpedoes with different infills, you see other torpedoes with different patterns cut in half. And then I use multiple torpedoes to test underwater. So the torpedoes that I found that would be neutrally buoyant underwater was at 65 infill. And then on the bottom, you see the torpedoes that are going into the competition along with the AEB. Next slide. And I will be handing over the camera time to my colleague Nahom, who will be delivering the simulation.
Thank you, Mr. Lares. So the purpose of the simulation is that we want to develop a virtual physics-based environment to support the rapid testing and evaluation of the autonomous utility vehicle, particularly from the software controls perspective. This is so the CS team and the software development can keep it moving forward, while the physical robots, mechanic and electrical hardware is still being developed. So on the left, you see an example of our inspiration, particularly from Project Dave, an open source project in ROS, robotics operating system, where you have an autonomous robots underwater, and it's actually a demo that interacts with objects with a claw and functional thrusters. So it's meant to be an iterative design process such as illustrated on the right. Next slide, please. So the main objective, right, was to have, by the end of this spring, a virtual twin of the autonomous utility vehicle to predict the vehicle performance. The inputs being the software controls, and we can also look at the hydrodynamic data from there. So the deliverables were determine the means of analyzing the model data, inserting the robot of this year into ROS for evaluation, implementing the competition obstacles and mission as well, as seen on the right. And then using part of the motivation was using ROS was we can have still a physics-based engine for implementing sensors as well, getting feedback there. And using ROS would eliminate additional steps where the code that's in ROS for the controls would have less processing to get it into the robot than per se if we use something with like MATLAB. So that was the advantage of picking Gazebo ROS. And that also provided the opportunity to go into low-level C++. Next slide, please. So the day in the life of the workflow to keep it high level was a lot of working with the terminal. There's a big time taken in installing the software and also starting off with our inspiration project Dave. It's an open source project that's you see on the left side of the figure. And that's where it took a lot of inspiration to begin the project. Next slide, please. And the big highlight there and milestone was, start this video, please, was to have a working demo of a robot from Dave that actually moves around with the ocean floor with some physics based on water and the actual mechanical properties of the robot. So we set it to some fixed velocity for pitch and yaw and the thrusters, and we got it moving in a circle, which is a big achievement. Next, this verified the proof of concept. Next slide, please. And the next big steps there, we're actually getting the robot into ROS, our robot, and having it function. That's where a lot of troubleshooting came in. So if you look at this figure on the right, you see that once we had to like take this CAD file, convert it to an STL, then mesh it with Blender and then put it in there. And we had issues such as half the thrusters not working. The thrusters or the arrows that are the blue arrows pointing up indicated the thrusters that worked initially. And then the red arrows that are the red X's are thrusters that didn't work. So you had this weird robot that was just moving up as you see my hands and they weren't really behaving to what we expected. So we had to verify that the model data that we pulled from SolidWorks along with basic hand calcs actually made sense. And then from there, we actually had thruster positions that were rectified and a robot that better behaved, that better followed the laws of physics. Next slide, please. So our final achievements in this semester were setting up a model of the robot, setting up world models of the robot to simulate the underwater fluid hydrodynamics, to set up a custom ROS launch file for rapid development of simulation, and to set up a thruster configuration as well. We're in the process of linking the sensors to the robot, particularly the DBL, IMU, and the camera. We also set up linear control of the robot, and in progress is controlling the rotations of the robot. The best part about this platform is that it exists. It'll exist for future RoboSub team, senior design, and club to develop their control software while mechanical hardware is being developed in parallel. Thank you very much, and I pass it on to Aren Petrossian.
Yeah, okay, thank you, Nahom. So for the intervehicle communication task, 1,000 points are given in the competition for teams whose 2 AUVs are able to communicate with each other. The communicated data could be anything from a simple Boolean to floats of XYZ or yaw pitch roll orientation values. Previous years from Cal State LA haven't attempted this task, but the 2 most common ways to do this are with blinking LEDs and with sound waves or acoustic waves. And so because the points are based off of the sophistication of the communication system, we decided to go with the acoustic waves. And the main effect that's going to be used is the piezoelectric effect that's shown in the top right. For the system I'm making, my requirements I set are to have a data transfer rate of more than 100 bits per second, to be able to communicate more than 50 meters from more than 50 meters apart, to have a small transmitter size, and to have a frequency range somewhere between 50 to 115 kilohertz, which came from competition rules and other sensors interfering. So on the far right here, you can see a PZT cylinder, which is the core of the device I made. This cylinder takes a voltage as a wave and gives out a sound wave at the same frequency of the voltage wave. I looked at various different PZT options and decided to go with the Steinmink 65 kilohertz PZT. For this PZT to work, I had to encase it in epoxy. But to do this, I needed to make sure the PZT would be centered inside of the epoxy. So I made this, I decided to make this mold along with the 2 spacers out of PTFE, which I'll machine using a lathe and a mill. Machining the spacers on a mill requires a support jig that I show in the bottom left. And this was a 2-part jig where I just screw the lid on and hold it in place while the mill runs. This is a photo of just the machining process, making the parts and putting everything together. If I skip to the next slide here, I can show on the bottom left, this was the completed mold assembled and put together. You can see the mold on the outside and the PCT sitting between the two spacers. In the middle, you can see one wire that's soldered to the inside of the cylinder and one wire that's soldered to the outside. This allows me to apply a voltage to the material. And on the far right, you can see the mold that I took with the PCT inside filled with outgassed epoxy. I took this photo on the right, the outgas epoxy filled mold, and placed it in an oven for a few hours to cure at high temperature, and ended up with the photo on the far left here, which is my cured transducer. I had to take the physical transducer out of the mold, and after a bit of grinding and sanding, I ended up with the 2 photos on the right, which was my final finished transducer. To actually power this transducer, I had to come up with a power circuit option that would let me give it a high voltage sine wave. So I looked at various circuits shown in the top left and found the R15-100B boost converter on the bottom, which takes our battery voltage and outputs up to 130 volts. With this in mind, I designed the power circuit shown on the top right and took this and put it into LT Spice in the bottom left and designed that circuit. To verify that it works, I ran the simulation and saw that when I input a 100-volt square wave, which is the top right photo, I end up with a 100-volt sine wave, which is my bottom right photo. And those would be the points on the far left and then on the far right of the circuit. So I took this circuit, since I knew that it worked, and put it into KiCad and designed a PCB around it, and there's a render of that on the left. And then I took my transducer with off-the-shelf components, like with an oscilloscope and function generator, to a pool, and I put my transducer on one end and the hydrophones, which is like an underwater microphone, on the other. And I was able to send a single pulse, which you can see in the top left of the MATLAB figure. And that's the raw signal that the hydrophone received. And then in the top middle, you can see the frequency domain of that. So you can see I sent 80 kilohertz and it got a massive peak right at 80 kilohertz. And then in the top right, I filtered that data with a simple bandpass filter. And everything seemed to be working perfectly. In the bottom, I enlarged the ping that you see in the top right. And I did a smooth envelope around that. And finally did a binary envelope of just 0 or 1 to say whether or not it got data. And everything seemed to be working perfectly. We were able to get data from 30 feet away. And I'll pass it off to Anthony to talk about the power distribution.
Hello, my name is Anthony Zelada, and I worked on the power distribution board for RoboSub. Our power distribution board is designed to step down from an input of 14.8 volts to an output of 5 volts and 9 volts. This is for devices that can't be powered directly from the battery because the voltage is too high. On the left, I have a table of all the targeted devices to be powered, and on the right, I have a map of the power distribution throughout RoboSub. Next slide, please. The beginning of the design started with the review of the previous year's team's design. Last year's team selected the LT3976 buck converter because of its high efficiency. A buck converter is a main component that makes the power distribution board possible and steps down the DC voltage to make it usable. Another point was I researched other buck converters and selected a high current, high efficiency buck converter called the MP8771. This was due to many devices that are being powered by the distribution board and would reduce the size of the board because I would have to use less buck converters. I also researched methods of constructing the board and what would be the best way for the board to be constructed, methods such as the polygon pour versus the trace width and how they could be used together, And also connection purposes, I looked up Molex connectors and how they could be able to power the board. Next slide, please. At the end of the first phase, I had most of the plans of the board figured out, and I would use the 3 buck converters, 2 MP8771s and 1 LT3976 to power all components. I also had both circuits designed and selected for the buck converters, and I made a power budget to calculate the power which the board would supply to the load and draw from the battery and the overall system efficiency. Next slide, please. At the beginning of the second phase, I entered some setbacks during the project. The MP8771 buck converter that I selected went out of stock and I had to redesign. To keep the board small, I ended up choosing to move the teensies over to the motherboard, a Judson TX2, and also program the RoboSub not to use more than 1 servo at a time. This way, the most current the board would draw at one time is 2.5 amps, which is optimal. Also, due to the time constraints, I decided to move on to the fabrication process of the board. This was instead of finishing the prototype board. The prototype was going to be used to check make sure the simulation works with actual components, but it was unnecessary. Next slide, please. There were 2 crucial software programs that I needed to be able to complete our power distribution board. I had to use one software to simulate the circuit and confirm that the circuit design from the data sheet of the buck converters would be correct, and tune the output of the voltages. The 9 volts was not given in the circuit diagram. The software I used for this was LT Spice. I had to use another software program to produce a blueprint of the PCB power distribution board would be printed on. This was used to give something to the manufacturer so they know exactly what to print. This software I used for this was called KiCad. I have LT Spice on the left and KiCad on the right. Next slide, please. The finished design was my first version of the power distribution board. The one on the left, the picture on the left is a PCB layout in the board, and it shows how all the components are connected. I had to select all the components. I had to assign the representation for them on the board and arrange them in a compact fashion that also still provided a good flow for the power. And on the right, I have a picture of what the power distribution board should look like after everything is soldered to. This is rendered because the board is still out to be ordered. As soon as it gets back, the only step left is to solder all 90 components to it and hook it up to the RoboSub. Thank you. I will be now handing it off to Cristian, and he will talk about the hydrophones. Thank you.
Thank you, Anthony. Hello, my name is Cristian Mota, and I'm in charge of the hydrophones. A hydrophone is an underwater microphone usually used in deep sea exploration, but for this competition, we will be using it in order to detect different pingers that set off frequencies ranging from 25 kilohertz to 40 kilohertz, set out at different depths throughout the pool. In our robot, we will specifically be using an AS1 hydrophone. This is perfect for our purpose, since its frequency detection range is from 1 hertz to 100 kilohertz and can be submerged up to 250 meters. And the pool that we're going to be doing the competition in is roughly around 40 feet, so it's more than good enough. And each of the hydrophones weigh 8 grams. We'll be using 4, so it'll keep our robot light. Next slide, please. So originally, the previous years were using a MATLAB code. They were using 2 MATLAB codes. One was for frequency detection, which detected the frequencies from 25 to 40 kilohertz, and they used a Butterworth filter in order to determine the max frequency and then take its FFT. And then the second code was to find the angle and distance of the pingers in order to perform the phase shift. On the right here, we can see the block diagram or the MATLAB code and how it works. It creates a sampling rate, you set the time, you pick up the data from the hydrophones, you apply a filter, you find the max of each hydrophone, you identify and extract the pulse data, you take the FFT, and then you compute the phase shift. On the left side, you could see the magnitude spectrum of the FFT picked up by the hydrophone. Next slide, please. So for this year, since we're using a TNC board instead of an Arduino, we're gonna be running the code directly. We're gonna be getting rid of the DAC system since we're gonna be running it directly from the TNC board. This is beneficial in two ways for us because now we have to change the code into C++, which is better for real-time response. And we also get rid of the DAC system, which decreases the weight of the robot by 157 grams. On the right side, we could see the block diagram for the frequency detection code. The TNC board processes the data picked up by the hydrophone. We initialize vectors for the pulse data. We filter it. We then store that filtered data. We find the max frequency. We take the FFTs of those max frequencies. We take the Butterworth filter. We Butterworth filter it, and then we print that data. And then on the left side, we can see the block diagram for the cross correlation of the angle detection. So we filter the parameters. We read the information from the TNC. We filter that data. We determine the angle and the time of arrival. We convert that into. We convert the heading by 360 degrees clockwise. We print the heading, and then we keep doing it for all the frequencies that it's picking up. Next slide, please. So there's multiple digital signal processing techniques that we could have used, but the best fit for our task is to use the FFT. Since the hydrophone picks up the information in intervals of time, we can convert that information into frequency domain in order to determine the magnitude of the signals. On the right side, we can see how it takes frequencies in time domain. It takes signals in time domain and then it converts them, it reads them and frequency domain. And on the left side, we could see the FFT of the hydrophones. It's the right side of the picture, and then on the left side is a filtered FFT. Next slide, please. So once there's just like with signal processing, there's multiple filtering techniques that we could have used for our code. We went with the infinite impulse response because it's best for audio equalization and their low latency, making them faster and better for our task. And then there's multiple infinite impulse response filters that we could have used, but we went with the Butterworth because it gives us a more smooth outcome of our task. And I will be passing it on to Edgar. Thank you.
Thank you, Cristian. Hello, my name is Edgar Brito. My task was to set up one of the navigation sensors. The Doppler velocity logger is a phased array sensor. The purpose is to provide position and velocity to the AUV, and it accomplishes this using the Doppler effect. It takes the differences in frequencies from the four beams and relays that difference back to the ship, and that determines its position and velocity. It operates at 614 kilohertz. Its minimum depth is 8 inches, and it can reach up to 200 feet. Next chart, please. The Pathfinder processes data in real time and provides this in raw files called PDOs. It provides this to the IMU to process. It contains ocean variables such as depth, velocity, and temperature. These variables are stored together in ensembles. And the graph on the right represents the data structure breakdown that's collected for an ensemble. Next slide, please. The DVL's minimum requirement is 8 inches of water, but it requires a bit of space, not just that minimum depth. Using smaller containers, we would get feedback from the beams and it would get an error result. It operates on a serial and internet interface, Ethernet interfaces, but Ethernet is required for C++, which we will be using. Next slide, please. The AUV will have a set pathway for the competition, with the DVL providing data to the ship's navigation systems to be filtered. The AUV will require other motions such as pitch and yaw from its inertial measurement unit. The chart on the right represents the flow of information from the DVL to the IMU. With the device's high accuracy, it should allow it to complete the competition task with better success than previous years, which relied mostly on computer vision and ship's IMUs since they were not using the Pathfinder at the time. Thank you for your time, and now for an acknowledgement for our sponsors.
Okay, thank you, Edgar. Yeah, so before we finish, we just wanted to quickly acknowledge some professors and faculty and staff from Cal State LA, Dr. Thorburn for advising our team for the second semester, Dr. Shen for advising our team for the first semester and half of the second semester, Dr. Tafunction for always being there if we ever needed assistance, Professor Cross for advising the CS side of our senior design team, and Professor Blake for helping with all of the machining of the frame and the hull. And lastly, also, of course, the Office of Naval Research and all of our other sponsors. Thank you.